So this is the last talk for the day. So I have the onerous task of keeping you awake. And I need to plug in this thing which goes somewhere. Yeah, I mean, we'll skip that. So this is a quick dive into program analysis. So let's hope we escape unscathed after the dive. So just to give you a brief introduction as to who I am, I'm a PhD student at the Programming Languages Lab. And by the way, thanks to Lars for the nice introduction. I hope I'm able to live up to this. So essentially what I work on is called static analysis of concurrent programs. So my PhD work essentially opened up a class of algorithms which analyze these programs fast. And hopefully we'll get an idea of what static analyses do. And so much of this, of the programs that I'll be demonstrating, they're all available at this link. And you can feel free to email me at this email address if you have any other queries. So why should we bother to analyze or verify programs? So typically when I was in my undergraduate and I heard the term, testing, and that was like the lowest rung of the ladder. That was the idea I had. But why bother analyze and verify programs? So the idea is that not every kind of fireworks is desirable, right? So as it turns out, you have this. I mean, there's no audio, but anyway, you will get the idea. So this is the Ariane 5 rocket launched by the European Space Agency, and as you can see, it lifts off, and it's tilting and. So it's gone. So what do you think happened here? So what do you think is the cause of this crash? Any guesses? Okay, so I could hear some kind of overflow, but essentially it crashed on June 4th, 96, and the reason was it was trying to do a conversion of a 64-bit floating point number to a 16-bit integer value. And essentially what we want to do is capture issues like this before the rocket explodes. And you can actually read up this book, which has quite a bit of detail about this bug and how it was actually flagged, but unfortunately after the rocket crashed. So a slightly more serious with respect to humans, because lives may sometimes depend on it. And maybe some of you may recognize this. Well, someone had a bright spark and said, well, we can actually automate radiation of cancer patients, right? So this is a machine called Therac25, and it was supposed to automatically give radiation to cancer patients. But as it turned out, that 6 patients died because of radiation overdose. And the reason was that it started providing high power electron beam instead of a low powered one, because the earlier models had hardware interlocks. But Therac25 depended on software interlocks instead. And there was a condition called race condition, right? So you might have heard of races, data races. And data races are very hard to detect and very hard to replay and very hard to even debug. But as it turns out, they can have catastrophic consequences. So 6 people died because of something called a race condition, which is a purely software bug. So you kind of get the idea why we should be analyzing programs. So the thing is that software today is ubiquitous. Everywhere you see there is some form of software or the other, even in places you might not want them to be, but they are everywhere. So an incorrect software could potentially have catastrophic consequences. They can range from financial losses to loss of lives. And you really don't want incorrect software in such like critical places. So essentially what our lab does is to design techniques which formally analyze and verify programs. So we don't want to arbitrarily test. We want to have some systematic ways of reasoning about programs so that we can give some formal guarantees. And the outcome of this analysis can either improve the performance of the program, or we can ensure that it doesn't do something bad, right? So you all actually use some form of static analysis. Every time you compile a program, the compiler does a bunch of optimizations. It removes dead code. It makes sure that it can minimize the number of memory loads. It does a bunch of analyses which are all static, which happens while you compile the program. But we want to design more static analyses for sequential and concurrent programs. So what is an overview of this talk? So essentially explore static analyses. And along the talk, I'll ensure that we build our own static analyzer along the way, right? So this is like a wake up kind of a step. And this is more of a demo talk. So we'll actually be testing it out on a tool called RatCop, which I developed as part of my PhD. So we'll have several demos throughout the undergraduate summer school, but I'm not sure. So most of these tools are third-party tools, right, which people will be demoing. So this is like a pure homegrown tool, like the previous ones which Professor Natarajan demoed. And so along this presentation, you have these slides, you have these demos, and you are an integral part of this presentation. So I'll expect your participation. So abstract interpretation. So this is the key behind doing static analysis. So actually, you're all actually familiar with the general idea of abstract interpretation. So let's say you have this problem in physics, right? So you have an inclined plane and you have a ball, and you're rolling this down, and you must have done this like any number of times, and you want to compute various parameters of this ball when it reaches here, like velocity, acceleration, what's its kinetic energy, and so on. But if you're given an actual inclined plane and a ball, then it's very hard to do so, right? Because there are a lot of parameters which make the computation really hard, right? You might have friction, air resistance, and so on. So what you do is actually, so this is too hard. So you actually do an abstraction, right? So you assume things like the ball is a rigid body, right? So there's no deformation. You make an assumption like, this plane is, maybe as a starting assumption, you remove friction. Or even if there is a friction, you say that there's a fixed coefficient of friction, right? And you make a bunch of such assumptions, and then you compute your values, and this is essentially an abstraction, right? So you compute a bunch of values here, and what you compute here is good modulo your assumptions, right? So if you say, oh, well, maybe I need to compute something more precise, then you would have to refine your model a bit more. So this is actually abstract interpretation in action. So we want to do the same thing for computer programs. So let's say you have this very simple program, which I don't know why you will write it, but for the purpose of slides, let's see, you have a variable which is initialized to 0, and you have a condition here which checks that I should be greater than or equal to 0. You increment I, and you want to check that I is always greater than or equal to 0 at this point. So what is one way of doing it? Well, let's just run the program. So I start I with any value, but I know that after I execute this statement, I is definitely 0 at this point. Now I execute, now I know that this fact passes this condition here, so this fact will propagate inside. And now I increment I, so I is 1 at this point. And now I have I here, which goes back here. So I had I equal to 0 initially, and now I'm getting I equal to 1 from the previous iteration of the loop. So I say, well, I could be 0 or 1 at this point. And now I continue with yet another iteration, and I'll say, well, I can be 0 or 1 at this point. Now I'll say I is 1 or 2 at this point, and so on and so forth. I keep on doing this. So when do I stop? You never stop, right? So you never stop. So you keep doing this forever, right? So this is called the concrete semantics. So this is given a program. The concrete semantics is the most precise meaning of the program, right? That's what it says. And in general, it is incomputable. Or even if it is computable, it's very inefficient. As you can see that you have to do a lot of computation. And what we want to do is, like the situation in physics, we want to do some form of abstraction. So what abstraction would we do? Well, we know that the issue here is that the variable I is taking values from an infinite domain, right? So, I mean, I'm glossing over the fact that this is like machine integers. It's not infinite actually, but let's assume mathematically it's an infinite domain. Do we really need this degree of precision to prove our property, right? We're only trying to prove that I greater than or equal to 0. I don't need to individually check if I is 1, 2, 3 or whatever. So what we want to do essentially is over approximate the values of I at any program point. And this solution is property driven. So what do I mean by that? So I know that my property here is I greater than or equal to 0. So what I'm now going to say is, I don't care about what the actual values of Y is at each point. I'm going to define what is called a lattice here. I'll just come to that a little later. But essentially what I'm saying is, at each point, I can only have these 4 values, one of these 4 values, and that's it, nothing else, right? So can anyone tell me, like, what does I less than 0 mean? What if I at a particular point, I write that I is less than 0 here, what does it mean? Right? So it means that I can only be negative at that point, right? So the concrete valuations of I at that program point can only be negative, right? So associated with every fact at this point, you have an associated bunch of concrete states, right? So for example, what would top mean intuitively? What do you think top means? Well, top means I can assume any value, right? It can be positive, negative, zero, anything, right? Similarly, greater than equal to zero means that I is only positive, and bottom means that empty set. If I annotate a point with bottom, it means that that point is actually unreachable, right? So no state can arise there. So now what I need is, let's say, so I know that if I is 0 here and I execute I++, I'll have I equal to 1 there, right? So now I can only annotate each program point with values from here. So now I need to say how each statement modifies this state, right? So if I have I less than 0 and I execute I++, what should I get as output? What? Sorry? No, but less than equal to 0 is not a valid state here. So I said that at each point I can only have one of these 4 facts. So what should I annotate? Really? So would that be correct? So if I is, so let's see, if I is minus 3, someone said T, but that is the right answer. I don't know who said T. Oh, good. So you're awake and you're correct. So if I is equal to minus 3 and I execute I++, I would get I equal to minus 2. But if I is minus 1, then I is actually 0, right? But that's not captured by anything here. So the best I can say is that it's T, right? So that's the correct answer. So good. Now if I execute, so if I start with I greater than equal to 0 and I do I++, what should I get? You should get I greater than equal to 0, right? So, okay. So yeah, right. So this is the idea. So this is, you've got the basic idea. So now I'm just going to execute the program with facts from this lattice. Just ignore this point. You can think of it as a set with an ordering. And now let's say I do the computation and I'll get facts like this at every program point. And this is efficient. I just have 4 values and I just have like a few transfer functions, and this is fast, right? But do you notice something strange here, right? So the strange fact is, I know that at this point, for example, or at this point, I can only be 1 or higher. But that's not a fact in this lattice, right? I can only say that I greater than equal to 0. And that gives us the key point of static analysis. It's going to be sound in the sense that it's always correct, right? If I was ever negative, then it would not have said I greater than equal to 0 at this point. But it could be imprecise, right? In this case, it is imprecise, right? Because at this point, I is actually just, I can never be equal to 0. But that's fine. We can handle this level of imprecision with some engineering. But this is the general idea. So actually, tools based on static analysis and abstract interpretation is quite widespread. So every time you get on a flight which is an Airbus, so much of that code is actually verified by a tool called Astre, which is an abstract interpretation based tool. As a matter of fact, Boeing recently found a bug which inside a flight reboots all the computer. That was found some time back. So yeah, I mean, Indigo uses Astre, so I'm not more like being sponsored by anything. But yeah, I mean, Airbus is safe, hopefully. So Facebook has a bunch of tools. Flow is, I think it's a type checker. Infer is an interesting tool which checks for memory leaks. And Ratcop is the tool that I developed. So there's a bunch of tools. And I think Infer has been open source. So you can actually go ahead, download Infer, and you can play around with it. Astre is not open source because it's been taken over by a company which does it for Airbus. So let's, so this analysis that I did earlier, it's called an interval analysis. So essentially, you want to find the bound of I. So saying I is greater than equal to 0 is equivalent to saying that I is in the interval 0 to infinity. So it's just a fancy name. So the tool that I've developed is called Ratcop. So it infers these relational properties. It infers relations between variables, right? And it's very efficient for this class called data race tree programs. So it's got a lot of analysis implemented. It's easy to set up and easy to use. So feel free. And it's 5 orders of magnitude faster. But let's just look at how this tool works. So essentially, let me switch somehow to this screen. And hopefully we'll be able to do this quickly. Whoops, doesn't come on the screen. Um, okay, this should fix it. Yep. So this will be a very quick demo. So modulo my computer speed. So right. So this is the let's look at the program we just looked at. Um, so this is the program we just looked at, right? So we have I equal to 0, and you have an infinite loop which essentially increments I. And now let's say that I want to prove at this point that I equal to 1, right? So let's say this is what I'm trying to prove. So all I have to do essentially is let's look at how it works. So you essentially tell it which program to run. In this case, it's called interval test. And I have to tell it to use the interval domain, which is 3. That should be fine. So now the widening you can ignore. So now what every static analyzer needs to do is infer certain things about the program, right? It doesn't know anything about the program. So it goes ahead and builds a bunch of graphs, pointer graph, call graph, to figure out what methods are called, which object is pointing where. And this computation takes a bit of time. So this is what's happening here. Uh, Okay, so now we can ignore this. So essentially it tells you that you have one assertion where you're checking that I greater than or equal to 1 and one of them passed, right? So this is the way the tool works, right? So essentially it picks up all the assertion, does the computation, and checks if the facts at that point imply your assertion. And it's as simple as that. So if time permits, I'll actually experiment a bit more, but I just want to switch with the slides. So how do we over approximate? Now that is the question. So we have a program and we have a property, and how do I over approximate, right? So as it turns out that you have several candidate solutions in hand, right? And the one you choose actually depends on the kind of analysis you're interested in. For example, here I was interested in proving properties like this, right? That something is greater than or equal to 0. So I would pick an analysis which reflects the shape of the property I'm trying to prove, right? In that case, I'll pick an interval, right? So here I'm trying to prove some interval, so I pick an interval analysis. If you want to prove that a pointer is never null, you would pick a different kind of analysis. So it depends on the property that you're trying to prove. So the solution is entirely property driven. So once you have the property in mind, you set the analysis up and everything else is automatic. You don't do anything else. So now, before we go into how we develop the analysis, let's look at how we formally look at programs. So a concrete state is essentially a snapshot of your RAM, right? So let's say you have two variables, X and Y. So one snapshot could be X is 0 and X is 5, right? And now you have something called a concrete transformer, which basically mutates the state. So if I have X equal to X plus Y and I apply it on the state, I get X is 5 and Y is 5. So mathematically, a concrete transformer takes in a concrete state and outputs a set of output states. Can anyone suggest why it's a set of output states? It's not just one state to another state. Why is this a power set? Not really. So this concrete transformer, right? So I mean, why would I get a set of states out here, right? So I'm taking a state as input. I should get another state as output. Yeah? Not exactly, but you're along the right lines. But so the idea is there are some instructions like x is random, right? So you can say, x is some random and you want a random integer, right? You cannot assign a fixed output state. You execute it once and you can get one state. You execute it another time, you get another state, right? So you have non-deterministic statements as well in your program. That's why you need a set. Another situation that may arise is that you have a condition and your incoming state does not satisfy. In that case, you have to say that my outgoing state is null, right? So it's the null set. So then for that, again, you would need a set of states, right? That's why you need this non-determinism. So statement prime is basically is the one you were talking about. It's a collection of states. So it's just it's a set of states mapped to a set of states. So you basically take each state in your input and you apply this function, this stmt function, and you collect. So it's just extending the stmt function to sets of states. And that's my concrete transformer. And that is what's called the concrete semantics. So this is the most precise meaning you can assign to a computer program. So the building an abstract analysis is just making the same analogs. So for each concrete state, you need to have an abstract state, right? So in our earlier example, you had this I less than 0, right? So that corresponded to a bunch of concrete states, right? So for each set of concrete states, you need to have an analogous set of abstract states, right? So that's the first thing we need. We need a domain of over approximated values. Is that enough? What else do we need? So in the concrete, you know that if I give you x equal to 0 and I do x plus plus, I'll get x equal to 1, right? I have these concrete transformers. I need the analog for that in the abstract, right? So I need to tell you that for each abstract state, how does each statement evolve or mutate that abstract value? And we just did that. For I less than 0, if I do I plus plus, I'll get top, right? And that's what's called an abstract transformer, right? So the two things that we have so far is for each set of concrete states, I have an abstract state. For each concrete transformer, I need to define an abstract transformer, right? So these are the two components. So the transfer functions map each abstract value to another abstract value. So is that enough? Well, let's go back to this control flow graph and we see a funny situation here, right? So let's say you have this data flow fact here and you have an incoming data flow fact here. So what is this section? This is a loop, right? So there's an incoming value for the loop and there is a value of the loop that I'm getting from here. What should be the abstract value at this point? What is that operation, right? So let's say I have I equal I, so I have I less than equal to 0 coming in and suddenly I have I, so this is I greater than equal to 0. And I have I less than 0. So the loop does something that suddenly makes I negative. So what should I infer about the point here? I come in with a value which is greater than equal to 0, but then something happens in the loop and then it makes it negative. So what should I say at this point? Right? Anything can happen, right? Because I suddenly make I negative inside, but I can come in with a positive value. So essentially anything can happen here, right? I could be positive or negative. But what did I do here? I actually took what's called a join of these two abstract values. I took a join operation. So this is like you have two sets and you take a set union, right? So set union is actually a join operation. So that is what we need. And for that, we would need what's called a lattice. So lattice is essentially a mathematical structure. So for that, you have something called a partial order. So you're all intuitively aware of an ordering relation. So partial order is given a set. It's a set of tuples which is reflexive, transitive. And instead of being symmetric, you have this property called antisymmetry. So if D is related to D prime and D prime is related to D, then antisymmetry says that D must be equal to D prime, right? So you have these three properties and you have what's called a partial order, right? And a lattice, so every, like gloss over the fact. So essentially an upper bound is, a lattice looks like this basically. These lines are partial order lines. You have a question? No. So if you join A and B, you essentially take it to D, right? So D is called the least upper bound. So if you look at it carefully, then this point also is a valid joint for A and B. But that's a little bit of an approximation. So the least upper bound is the most precise approximation of A and B. So that's what's least upper bound. So a lattice is that every pair of elements must have a least upper bound, right? But the question is that enough? This strange structure here where you take the set of natural numbers and they're ordered, right, by their natural ordering. And let's say I have an iteration like this where first I have 0, this doesn't increment, I get 1, then I increment, I get 2. So now, if you take any two elements, what is their upper bound? Let's say I take 0 and 1. What is their upper bound? It's 1. If I take 1 and 2, it's 2, right? If I take 0 and 3, it's 3, right? So every pair of elements has an upper bound, so it's a lattice. But what if I take the entire set of natural numbers? What is their upper bound? Right? It doesn't exist in the set, right? So this is a situation where I keep coming and I keep going up, and this is a situation where my analysis will not terminate. So what I need is called a complete lattice. So complete lattice extends this pairwise thing to a subset of elements, right? So you give me a subset of elements, and my upper bound is guaranteed to exist. So this is like if you just write, if you have 3 elements, or maybe an infinite number of elements, then this is your lattice structure, and you add an element at the top which is called the top, right? And the element at the bottom is called, it's called the bottom, yeah? So very creative naming. So you have a top element and a bottom element, and this makes it a complete lattice, right? And there is a bunch of mathematical properties which says that if your function is monotonic and and if you have a complete lattice and then you're guaranteed, your analysis is guaranteed to terminate even if you have infinite, even if you go up infinitely, then your analysis is guaranteed to terminate. So anyway, so this is what we need essentially. So not just a bunch of elements, but an ordering which satisfies some properties, right? So in this case, a complete lattice structure, right? So this is what we need. We need a complete lattice of over approximated values, and we need transfer functions, right? And the final question is that enough? So because I'm asking, right, so it's not enough. So I also need what's called a concretization function, right? So I need to tell that for each abstract value. So I'm doing some abstract analysis, right? So now I don't want to sit on an ivory tower and do an abstract analysis and go away, right? I need to tell, well, what does it tell about my original program, right? But what does it mean to say something about the original program? It means to say something about the concrete semantics of the original program. So I somehow need to relate these two semantics, right? So for each abstract state, I basically say, well, what concrete states does it represent? And we did that just a while back, right? So for, let's say, I greater than or equal to 0, we said it's all the positive valuations of I. For I top, it's any valuation of I. For I bottom, it's the empty set. So I need what's called a concretization function. And as it turns out that if you give me a concretization function, I can give you an abstraction function, right? I can build it up. So it means that if you give me a set of concrete states, I can actually compute what is the corresponding abstract state. So as it turns out that this is enough, right? So you just need these 3 things, and so we have our analysis. So let's see if we did that for the interval analysis. So for the interval analysis, did we have a complete lattice? Right? So we had a complete lattice. So if you just go back, I'll go back very quickly. So this was my interval analysis. So I had a domain of abstract values, but is this a complete lattice? It is. You give me any set of values, right? You give me you pick any subset that will have a least upper bound, right? So because let's say I take this guy and this guy, its upper bound is stopped, right? So I have my complete lattice. Do I have abstract transformers, right? We discussed that. So we discussed that if I is less than 0 and if I do I++, I'm going to get top. And we discussed that if I is greater than or equal to 0, I do I++, I get I greater than or equal to 0. We have that. And we have also discussed the concretization function, right? So we said that, well, here is a concretization function. So we had all the elements, and that's why this is a valid abstract analysis. So these are the 3 components that you need, and we worked through it, and we got our abstract analysis, right? So now comes a part of the talk where you participate. So let's say we have this program, right? So now the question is, would the interval analysis work here, right? So I have three variables now. X is 1, Y is 0, and I is 0. So essentially, I have the same program as before. This is an infinite loop where I keep incrementing I. But the only thing I do is X is initially 1, Y is initially 0. Now, I increment X in steps of 2, and I increment Y in steps of 1. And I want to prove that X is greater than Y. So first of all, does the property hold here? Yes, it holds here. Now the question is, will my interval analysis be sufficient to prove this? What do you think? Well, for the first thing you need is what is my interval now, right? I have three variables, right? So you first of all, you have to think along the three things that we built, right? So you have to think about what is my abstract value now, right? So I built it for I. So what is my abstract value if I have three variables? I can just take a Cartesian product, right? So instead of having one lattice, you can think of having three lattices. One for I, one for X, one for Y. So now at any point, my data flow fact could be some like I is greater than or equal to 0 and X is greater than or equal to 0 and Y is greater than or equal to 1, right? Something like that. But as it turns out, it's not enough, right? So I'll give you a brief intuition as to why it's not enough. So if you look carefully at what the interval analysis does, it computes things like at this point here, at this point, X is 1, 3, 5, 7, and so on, right? And Y is 0, 0, 1, 2, 3, and so on. So the intuition why interval can't prove this is because you see that it's not tracking any correlation. So if you ask that, well, is X greater than Y? What it will do is, it will see, well, I can take a value of X which is 3, and I'll get a value of Y which can be potentially 4. So I'll say, well, this may not hold. You see, this is quite tricky to see, but this is what happens. So it's saying that X can assume the values 1, 3, 5, 7, and so on. So it's just inferring intervals, right? So let's be very concrete and say that the exact set of values of X is 1, 3, 5, 7, and so on. And the set of values for Y is 0, 1, 2, 3, 4. But if I ask if X is greater than Y, it must compare against every possible valuation of X and every possible valuation of Y. So in some sense, it's taking Cartesian product. So nothing stops it from taking a value of X which is 3 and a value of Y which is 4. So it can't infer this fact because it's already lost the correlation between X and Y. So if you run this program in the tool, I think I have some time here, so I have some time, yeah. So 5 minutes, and then so if maybe even less than 5 minutes. So right. So if you look at this program, so this is the same program that I wrote. If you try to execute this with intervals, yep. Yeah, maybe I should have started running this and then explain why it didn't work, because then you'll get bored. But anyway, so let's not get bored. So again, it's doing this bunch of things. So yeah, so what we need actually in this case is something called octagons. Now, this intervals and octagons, they're all shape of these invariants. So this is as you can go ahead and read the paper why they are called octagons. But essentially, we need again, we go back to the initial point, right? So we are trying to prove properties of the form X greater than Y. And we see that intervals are not strong enough to capture these properties. So we need an abstract domain which can in fact track these, right? So we'll look at the intervals here and it will say no. So this doesn't really take that long. So it goes and says, well, I don't think it holds, right? And the thing is, you can now go and take a look at The, so the good thing about these tools is it now generates what's called, it basically throws in the reasons it thinks why this property does not hold. And you can actually analyze this, and basically you can figure out that these properties don't infer the fact that x is greater than y. So let me ask a slightly different question. So it says that failed, this failed, that I0 minus I1 greater than 0, right? So it's essentially doing x minus y greater than 0, but it's saying I0, I1. So why do you think this happened? Yeah, you're almost there. Exactly. So it's an intermediate representation, right? So the point is, if you go back and think about what we did, we had to define abstract transformers. Now, if your program has, as in the case of Java, it has nearly 200 instructions, then you're going to spend a lot of time writing these abstract transformers. So what happens is this original Java program is modified into an intermediate representation called Jimple. And this Jimple has only 15 instructions. So you just have to say what happens when these 15 instructions happen. And Jimple represents programs in 3-address static single assignment SSA intermediate representation, which basically renames your variable. So it basically says I want to do x minus y greater than 0, but it got renamed to I0 minus I1 greater than 0. And you can just think about this and see that this does not actually imply that x minus y is greater than 0, right? So it gives you a hint as to what went wrong, and then you can basically go and figure out what's wrong in the program. But the last thing would be, we just try to run this with octagons now, which can track variable correlations. So all you have to do is change the domain to 1, and now it tracks octagons. So now it tracks variable correlations. So all I did was, well, I'm trying to prove properties of this form. So intervals are not good enough. So I switched to an interval which is, switched to an abstract domain which is. So while this happens, another small quiz question. So I mentioned that intervals cannot track correlations. Is it always true? So can you modify this program slightly, somehow, such that intervals can now prove that x is greater than y? I explained why intervals didn't work, but that's not always true. What do you think, like if I modify this slightly? You can? Right. Exactly. So one simple thing is you don't modify y, right? So what happens then? That the interval of x is completely disjoint from the interval of y, and no matter what x you pick, the value of y will always be less. You see the point? Let's say you didn't modify y. So y's value set would just be 0, and x would be 1, 3, 5, 7, and so on, right? So now for any choice of x and y, you're guaranteed that x is greater than y, right? Another step is if you did y equal to y minus 1, right? Even then, you might have multiple values for y, but no matter what your choice of x and y, your value of x will always exceed the value of y, right? So it's not always true that intervals cannot infer relations, but it's a safe bet not to do it when you have these properties. And lastly, if we go back and see what happens here, it says that now it's able to prove that x is greater than y, right? So that's all I have. So I think I've finished on time as well. So I'll just summarize. So, oops, sorry. So there is another domain called convex polyhedra, which is even more precise than octagons, but as it turns out, it's slower. But what's interesting is, so there was a conference very recently which I went to, and there have been people who worked on this. So the reason why people don't use it is because it's very slow. But suddenly someone comes and says that, well, here is an algorithm which makes this a few orders of magnitude faster than what we do at present. So I mean, exciting things happen all the time. So please feel free to download this tool and play around. Uh, so that's it. So what I tried to put across in this talk is a formal way of arguing why programs are correct. So we have a program, we build a mathematical model out of it. And as you can see, there is a blend of mathematics and programming, right? So you have to essentially abstract your program in a way which is amenable to mathematical analysis. And then you need to go ahead and program it such that you implement and figure out. There is a fair amount of engineering involved. So sometimes you don't get the precision and you go and figure out, for example, in the case of the Airbus code, so they wanted zero false alarm, no false positives. So they had to go deep into the code of the Airbus. It was easy for, I mean, not easy for them, but some things made it easier because in embedded system, you're not allowed to have recursion or dynamic memory allocation. But under such cases, they wanted to be having zero false positives, and they did that. So there's a fair amount of engineering involved, and that's it. So thank you for your attention, and I would be happy